abstraction on something. Now, what that means is different needs. Then we have this notion of control plane. There's an API, Kubernetes, and on the right-hand side, we have things like data centers, like our data center in Township of Iowa. We have potentially a Kubernetes cluster on Raspberry Pi, a bunch of Raspberry Pis, which like to get that's just there for fun. We built this, we helped build it with labs there. Then we do the cloud platform. So I think that's an important summary of what Kubernetes gives us. We're not going to talk much about the architecture of Kubernetes in this slide deck. We set out that we are basically looking at a master slave system or master node system. And nodes where in a cluster, they can be on premise, they can be in the cloud, they can be on a Raspberry. So I'm not going to use this graphic to explain Kubernetes, let's get into the details. So Kubernetes, what does it give us? So it helps decide where our containers should run. And when you have a container, all you have to do is tell Kubernetes, I want to run this, please run it for me. Maybe you'll provide other information about it and hook it up to other components and other abstractions that are running within Kubernetes as well. It manages lifecycle health of my containers, and we'll talk about the actual runtime artifacts with the Atom scheduling shortly. But it will keep containers running despite failures. And this is for some notion of containers. Containers are generally ephemeral and replaceable. Making sure that we have the right number of containers running at any given time is what Kubernetes will do for us. Also scaling, we want to be able to make sets of containers larger or smaller, depending on traffic or anticipated traffic. We want to be able to find out where containers are or where they're represented by services, where they're components of a microservices architecture or just generally a monolithic service represented by container. You need to be able to name them, you need to be able to discover them. And believe me, people still build monoliths and containers today. Load balancing, we want to be able to distribute traffic across some set of containers running on our cluster somewhere, our cluster infrastructure, and potentially even across a federated cluster today. We also want to be able to provide storage volumes to our containers. Everything needs to store data. We want to be able to log and monitor what's happening within containers. And Kubernetes also provides debugging from introspection, so we can actually look at containers, look at what they're doing, attach them, and debug them as needed. And the final part is make sure that only the people we want to be able to do something with our containers can do those things by identity and authorization. Excuse me, I'm coughing into the microphone. So that last part, a quick recap. Kubernetes is one of, at the end, 3 layers of cloud native. I'm not updated that, much more so cloud native. You can go to cncf.io to find out more about the cloud native foundation. But basically, we've talked about the architectures here and what it does, containing package apps and written microservice architectures. It's been around for almost 3 years now, GA since 2015, 1.6 is due in the end of March. We're currently at version 1.5. Less than half the code is now written by Google. I couldn't find the latest version of the graphic, but you can see there it's 44% of the and it's stewarded by the cloud native. Like reimagining what does externally. Uh, we're unlikely to port to Kubernetes anytime soon because we have so much dependency on it. But to build something from scratch outside of then this is what Kubernetes is effectively. We're guaranteeing that no breaking changes will be introduced until version 2 of V1, so that's important for everybody that uses it. We have different tracks for introducing new features, both alpha and beta. We have significant feature sets in beta currently, and obviously your GA tracks guaranteed certain levels of stability. We do thorough end-to-end testing through the community. We help with that as well at Google. And there's lots of new work taking place outside of the core commit process of Kubernetes. Most of this is accessible from the GitHub project. You can find out more about all of this ongoing work. Kubernetes also has a very solid core. We're going to talk about some of these primitives soon, not all of them. Pet set mentioned there, sorry, it should be stateful set. We'll cover that shortly. My voice is definitely struggling here. So these are the core concepts. I don't like talking about bullet points around individual things that may be complicated to understand. But we also do have a Kubernetes ecosystem is extremely healthy and is supported by very large companies, different distros, different cloud providers, different platforms of service offerings, continuous deployment offerings, various package managers, monitoring, networking, storage and appliances. This may not be up to date completely, but it's going to be more instead of less. And also we have great momentum. As of this morning, 43,765 commits to the GitHub repository and 1,078 contributors, including many important companies as listed below that number. So Kubernetes, we go back to a picture that looks remarkably similar to what we saw earlier with Borg and with our initial abstraction of what Kubernetes would look like. Our developers are accessing a Kubernetes cluster via a control plane, which is the API. Somewhere within the cluster we have machines. As a developer, we don't care what those machines or those nodes are. It's really only something that the control plane, which in this case is the Kubernetes master and scheduler, need to know about. So we have these servers, we have the control plane, and developers can access them via either the API, which is extremely common. This can be made use of by many third-party tools as well. You can use the CLI, the command line interface, the kubectl command, and other commands now. And also the user interface, which is still very much a work in progress. Many people like to build their own user interfaces in front of Kubernetes. That gives them a lot of flexibility and allows them to integrate Kubernetes by CI/CD into their own workflows. So the dashboard, the user interface has never really been a huge priority for Kubernetes. So ultimately what you do to get started with Kubernetes is you start with a cluster. You need some machines to be able to run this on. That could be as simple as a laptop. You can run Kubernetes today on a laptop, or you can run it in a high availability multi-node cluster. It can be hosted, or you can manage it yourself. We have an example of that hosting in Google Container Engine, and there are other distros as well that provide hosted offerings of Kubernetes. You can manage it yourself. It could be on-premise or cloud, as we've already established, and it could also be on bare metal or on virtual machines. Supported by most operating systems, and can just run on just a bunch of Raspberry Pis, which is something we did at DevOps last year with Quintor from Amersfoort near Amsterdam. There are many different options. There's a matrix down there, a link. I've not actually checked the link for whether it's still updated. I'm sure it probably is. That's good. I like that. But I should update that later. I'll share these slides with you afterwards. Setting up a cluster, there's various different ways of getting started. If you want on-prem, we've recently introduced the kubeadm command, which can be used to configure masters and nodes in an on-premise environment. There's also this thing called COPS, and I've not looked back on this for a while to see what kind of traction it's getting. But this was designed to specifically run on AWS, run Kubernetes on AWS, although the plan was for it not to be limited to AWS, but it does simplify deployment and getting up and running, because on some environments the networking is all taken care of for you. On AWS you have to run things like Flannel, that kind of thing, to be able to run Kubernetes, and COPS takes care of that for you. You can choose a platform, whether it's on Google Cloud Platform, Azure, Ubuntu, Juju, and you can just run it from the command line. You get the script. I wouldn't recommend using the curl command anymore. I don't think people do this anymore. I think it may still be in the docs like this, but you can specify your Kubernetes provider, pull down the script, run the script, and that will install Kubernetes for you in your environment of choice. You can choose a distro like Red Hat Atomic, Tectonic, Mirantis Murano, Mesos, or you can build from scratch. And there's a research for Kubernetes the hard way. One of our guys, Kelsey Hightower, has a walkthrough of how to build Kubernetes completely from scratch. Let's get into the abstractions of Kubernetes. And the first one is a pod of containers. We don't actually run containers, we don't schedule containers specifically. We have this notion of a thing called a pod. And this is probably the hardest thing to get your head around. It's fairly simple, but the biggest question is normally, why a pod? Why do we need this thing? Why can't we just schedule containers? And this generally really is kind of a mismatch between the way Docker works and the way the infrastructure works, and the way we need the infrastructure to work. We'll look at networking shortly. There are some things we actually require that were not available in Docker when Docker came along. So we have this abstraction called a pod. And a pod looks pretty much like a logical, a virtual representation of a logical host. Not a VM, but looking like a host and being able to run things like a host. It has its own IP address. It can run containers and mount volumes. Ultimately, we can run multiple containers within inside a pod together when there's a need to. This isn't the idea of building monoliths. It's not to facilitate building monoliths, but often you find containers need to run side by side. And we have various different patterns for that, often called sidecar containers or adapter containers, things that do things that offer value to the running container. We look at App Engine today, App Engine Flexible environment, which has a container and a Memcache container that runs side by side with it. And those containers will live and die together. So we have an example on the next slide, I believe. But they also support liveness and readiness checks, and they have post-start and pre-start lifecycle hooks that can help with teardown and creation. Here's an example of where we'd run multiple containers in a pod. In this case, we have a Node.js application container serving traffic to consumers via an abstraction we'll talk about shortly called a service. And we have another container that's running side by side within the pod that's monitoring a GitHub a Git repo. And whenever pushes are made to the Git repo, the Git sync container sees those pushes, pulls down the content, stores it on a volume, which we'll talk about shortly as well. And that can now be updated and served by the Node.js application container. Here we have a lifecycle dependency. Now, those things need to live together. They are matched together. And when one goes away, the other can go away as well. So it makes sense to run them inside a pod. They do simplify networking for us as well. And these containers share effectively port namespaces and IPC namespaces, and they can talk to each other through localhost, just like they're running on a host machine. So if you can imagine building this machine physically and just then mapping it to a pod and then pushing it out into Kubernetes to say, this is what that machine would have looked like, a virtual representation of that, now running as a pod. Pod networking is an important concept for us because there are some requirements that we have, and this where some of the complexity of Kubernetes comes in, which is generally going away with things like COPS, whereby we need to have a network layer that allows pods to have their own routable IP addresses that's unique within the cluster, which means we can actually access each of these pods individually by IP address or ultimately via a DNS lookup. That's extremely powerful. So these blue boxes here are nodes, and we have other dark blue services running within the node, but the pod is scheduled on the node. It has its own IP address, and these things can expose the same port. So like in the middle example, we have 10.1.1.2.11 and 10.1.1.2. They could both be exposed in the same port, both run on the same host, but because of the networking overlay that we use, that's perfectly okay. That's not a problem. We can schedule multiple pods of the same type, or each exposing the same port on a single node. And that's extremely powerful. So no brokering the port numbers at all. And pods can reach each other without using NAT, even when they're on different nodes. There are many different solutions, and again, I'll probably need to update this list a little bit. You can use things like Funnel, Weave, Calico, Open vSwitch, or you can make use of your cloud provider. And this is what Google Container Engine does, or when you're running Kubernetes outside the Container Engine on Google Cloud Platform virtual machines, you get this for free because it's supported by our network infrastructure. So that makes it very simple to use. So that's how pods work, and this is one of the reasons why we have pods, because of the networking. Ultimately, pods are built from some kind of spec template. Basically, this is something that can be recreated. They're completely fungible. They can be replaced. They're completely ephemeral as well, but they're functionally identical. And we just build a pod from a spec template that we created, and we can have as many copies of that, many replicas of that as we like across the cluster. We're going to get into more details of that and see some more examples. One of the powerful mechanisms, one of the much needed mechanisms within Kubernetes is a grouping mechanism called labels. And we can group pods, we can group other semantic abstractions as well, using these labels. Effectively, every resource within Kubernetes cluster can be labeled in some way. It includes nodes. And the most powerful abstraction you'll find, or powerful use of them, is with pods, where we're going to group pods together. So now, we mentioned that pods are created from a spec template. In this case, these two pods are functionally identical. They are fungible, they're replaceable, and they both have the same label, which means we can now build other abstractions, or tooling even, that can say, I care about all of the pods with the label type equals FE. And in this case, well, in all cases, labels are key value pairs. They have semantic meaning to you, but not to Kubernetes. Okay, so for the most part, there are some labels that may have semantic meaning to Kubernetes, but mostly not. In this case, you'll say type equals FE because you care about pods that are front-end pods, and you define that type. And now we can build a dashboard of some kind that cares about all of those pods, and you can make API calls to Kubernetes to say, give me all of the pods with label type equals FE. Or we can have another dashboard, and in this case we have version equals v2, and we built another dashboard or another abstraction that cares about version equals v2. Pods can have multiple labels, and they can be similar to this structure here. Then maybe there's some difference between the pod in the middle and the pod on the left, both of them are type equals FE, but this one is a later version of it, and we'll look at the canary and other abstractions shortly. These things are queryable by selectors, and you can do that via the API, or Kubernetes can do it as well. Then we have the notion of a replica set, and a replica set manages a number of running pods that are functionally identical, built from the same spec template we mentioned earlier. That's something wrong there with my picture. Yeah, okay, anyway. Normally I'm not convinced that that's correct because, well, maybe it would be, yeah, okay. So basically, when we create pods, we give them labels. We also have this ability to create a replica set. And a replica set will is an abstraction that comes up. We build a replica set. We tell it how many pods it needs, and we provide it with a template. It knows how to build pods from that template. So in this case, what we have is some kind of template. We're saying we want 3 of this template. When the replica set comes up, it looks outside in the cluster to see if there are pods that match that label. If it finds them, then it starts effectively managing their life cycle for us. If it doesn't find them, it will create them for us from the template. So in this case, this works. We have 3 different pods with effectively 2 different labels. The replica set probably didn't create all 3 of these. It probably created the first 2, and it is managing the last one, because it has a slightly different label configuration. But effectively, what we're saying here for the replica set is, I want 3 of these. This is my template. Please make sure there are always 3 of these running at any given time. And it will be effectively a control loop. We'll continue to monitor that. It will look to see if there are 3 of these running. If it finds there are 4 running, it will take one away. If it finds there are 2 running, it will add one. And it will use the template to create that. It is possible we can update the replica set, and we can effectively then tear down the pods and recreate new ones. That's a thing called a deployment, which we'll look at shortly. But ultimately, these things make sure we have a desired state. We used to use this term quite regularly, desired state. It manages that desired state. This is the state of the pods that we want to have running, and it will manage that for us. Deployments effectively take that one step further. What we used to be able to do is provide some kind of rolling update for a controller. Effectively, what we would have would be a replica set that managed a bunch of pods, and we want to be able to update each of those pods to a new version. That would involve creating a new replica set. In those days, it was called a replication controller, and we would basically tear down one pod from the old version and bring up one pod on a new version until we had replaced them completely. But that process was driven completely from the client side, from the actual kubectl, the command line tool. We'd do all of that work by issuing API calls, and it was completely interruptible, which means if you control-C'd it or something went wrong, it would leave the entire configuration in an unknown state. We may have X number of new pods and X number of old pods. We may even have the wrong number of pods. So what we did is move that inside the cluster via a deployment. And so deployments effectively offer updates as a service. We say how many pods we want to run. We provide a template, and we ask the deployment to manage that via a replica set. So now what we can do is we can roll out updates to deployment, say, hey, I've updated my configuration, here's a new template, or I want more of these, please do this for me. And the deployment within inside the cluster will take care of those changes. I think I have a demo of it soon, but I'm not sure. We'll get to it in a second. But anyway, effectively, they can manage changes such as rolling updates. They can do all the scaling for us. We can actually edit a configuration on the command line. We can issue a command called kubectl edit, which will pull down the configuration of the deployment and allow us to edit it. Once we have applied the changes, they will be pushed out to the cluster, and it will enact those changes by updating the pods within the deployment. And we can manage rollouts and rollbacks as well. This is a much more powerful mechanism, and it's completely managed on the cluster. Then we have the abstraction of services. My slide animation's broken a little bit. Pods can run anywhere within the cluster. Pods are ephemeral, their IPs are not stable. And we may have many replicas of the same pod running within the cluster. That's interesting, but how does that help us? We have this situation here. How do we get access to them, and how do pods find each other? We may have multiple microservices deployed within the cluster. We may need to come in externally to be able to find those pods. How does that work? And how do we route traffic to them ultimately? And that's done through something called a service. And so now we take this, the pod abstraction, they have labels. In this case, we have app equals backend. And we're going to stick this other abstraction in front of them called a service, which cares about pods with the label type equals FE, or sorry, app equals backend in this case. I need to update that slide. And then basically what can happen what will happen via a virtual IP provided by that service, other pods can find that service and access those other pods. External services can do that, and we can route traffic to them all via this virtual IP. And the virtual IP gets a DNS entry as well, so we can discover it via DNS. So this effectively aggregates all of those pods into a service. It may be a microservice, it may be a one-off service that we're running across the cluster, but this is the mechanism we use to be able to communicate with running pods within the cluster. Choice of the pod for routing is currently random. It used to be round robin, but we do support session affinity via client IP. And the virtual IP address is stable, as is the DNS name. Okay, so that's what a service does. We also have another abstraction or another version of a service called a node port, which allows us to, rather than having to worry about where the service is running and route traffic to it, we can actually expose a port on every single node within the cluster, and then that will be our service, and that will effectively route traffic to any running pod within the cluster. So we don't need to do discovery, we just need to know where the node is, and that may just be an IP address. So we point to a node, hit the port, and that incoming traffic, incoming request will be routed to a running pod within the cluster that exposes that service. There's also DIY load balancer solutions. The load balancer one is what we just saw. DIY load balancer solutions such as SOCAT, HA Proxy, and Nginx. And we also have this thing called Ingress. And Ingresses provide, maybe not in beta, I'm not sure. Some of these things, it's really hard to find out what's in beta and what's in alpha nowadays with Kubernetes. I should probably look into that. But basically the idea, we have two services and we have to access them via their own DNS names or via their own IP addresses, independently of each other. But maybe we want to route traffic through a single endpoint, and Ingress gives us that ability. In this case, we have two services. They have pods that they represent, which may be name equals foo, name equals bar, which is the label for those pods. When we route traffic to them, we have to go to the virtual IP or to its DNS name. What we can do with an ingress, we can stick this ingress in front of it, which will allow us to have a single DNS entry, external DNS entry, or a single IP, which will route traffic based on URL. And in this case, we have service foo and service bar having traffic routed them through the URL path foo and the URL path bar. So this is extremely powerful as well. This was introduced a while back. I also want to talk about scaling as well. We do this via a replica set, but also via a deployment, which manages the whole thing for us. We start off with one pod. We have a pod and a service in front of it. The pod has a label, version equals v1, type equals fe. The service cares about labels with type equals fe, and the replica set cares about label, version equals v1. It effectively provides that kind of diagrammatical form there. They are using different labels, and that's important when we look at canary and shortly. What we do is we say to the replica set, I want two of these. And now the replica set spinning again is control loop. It says, I should have two of these, but I've only got one of them. So it will now issue an API call, and we'll create a new version of that pod from the template that it has. Again, the same labels as before, and given that it has the same labels as before, which is defined as part of the template, the service will now pick up that new pod and automatically route traffic to it once it's online. And if we say 4 pods, exactly the same happens. We have an extra 2 pods, again the same label, and now we have 4 pods. The service is routing traffic across all 4 of those pods. And the next thing is a rollout. I want to kind of just go through this. Oh, my graphics are broken again. In this case, we have a replica set with 2 pods, version equals v1, and a service with type equals be. The service is the green box at the bottom. We're not going to worry about the service too much in this, but we want to be able to update the pods. Maybe we have a new version equals v2, and we want to roll out. And we can do this using something like kubectl edit deployment. In this case, we will issue that command. We may edit some factor of the pod template. In this case, let's imagine we're changing the image. So we built a new container image. We pushed it out to a repository, and now we want to, which could be Docker Hub, it could be our Google Container Registry. We run on Google Container Engine, but we now want to update our pods with that new image. So we edit the deployment. We could be doing this via CI/CD, and once the deployment sees those changes, it will be responsible for updating the pods. The first thing it will do will be create a new front end, a new replica set. The replica set will have a different name slightly. It's hashed, so it's created dynamically, the name. But it cares about pods with version equals v2. And initially it has no pods. And then we scale that up to 1. The replica set again spinning will say, oh, I should have one of these pods, my new template here. It will create the pod, version equals v2, type equals be. Again, it's aggregated by the service. The next thing we need to do is to downscale the existing replica set, and we take both of those away. We have here a situation whereby we only had one pod serving at any given time. You can control that. So like if you want, there's a thing called max surge and max overhead. I can't remember what it's called, but basically you can define how many you can have over the number you really require and how many below the number you really require. In this case, the default setting was to be 1 less, and what we had is a situation where we only had one pod running at one time. We could make sure that we always have 2 running by changing those parameters. But effectively what's happened now is we've replaced the running pods with 2 new pods that are built on the new image that we created when we edited the deployment. The old replica set will continue to exist. It doesn't take up much in terms of resources. It has no pods attached to it. If we ever needed to do a rollback, we would reuse that replica set. We could roll back that update and go back to the original configuration just by issuing one command. That's really powerful. And Canary is another situation where we find ourselves in. We may have 2 running pods, version equals v1, and managed by a replica set and abstracted out to a service. We may want to test an update to our container image. And what we can do in that case is create a new replica set, again, with one of the labels being type equals BE, so it's still aggregated by the service, and one label is being version equals V2, which means it's being managed by this different replica set. Now we're routing traffic between 2 different versions of our pod, V1 and V2. So effectively 66% of our traffic is going to the older pods and 33% is going to the newer pod. We can then decide at some point that the change that we've rolled out is good, and we can then update the deployment for the first replica set to use the new image. Or we can roll back and tear down the replica set and start again and try a different version. That's something we do often at Google. Canary, we have a very small percentage of our deployed services on the newer version. We can monitor how that's performing. If it's performing well, we can roll out the change across the entire application, or we can roll it back and go back to where we were before. That's very, very easy to do within Kubernetes. Auto-scaling is also extremely powerful. In this case, we have a replica set that manages 2 pods. This is an example I used at DevOps, which is why it's got strange labels. And we are monitoring the CPU utilization of those pods for a thing called Heapster, which runs as a pod within the cluster. This is all automatic. We get this for free. And we set a scale target of CPU percentage equals 50. What we're looking for is if the CPU percentage gets greater than 50, we want to be able to update or add new pods on demand. So initially the replica set is set to pods equals 2. We now have this loop whereby we're monitoring traffic. If at some point the CPU goes above 50%, which it has in this case, we will, via the scale resource, we will ask the replica set to add new pods. So we change the replica set number of pods to 4, and it will take care of running the new pods. And ultimately now the CPU utilization drops down below 50%, and we now have a stable environment. Whenever that goes, whenever we need to, we can tear down pods as well using that same mechanism. Scheduling, we mentioned scheduling before within the context of Borg. I'm not going to spend too much time on it. We've only got 10 minutes left. 5 minutes left. Oh, wow. But Kubernetes without a scheduler does work. You don't have to schedule things for Kubernetes. You can specify via this label here, a node name within your pod spec. I want it to run on a specific node. You could do that if you wanted to. That's not how you should do it. But that is possible, and that's how Kubernetes would schedule a pod if it didn't have a scheduler. But what we do have is a scheduler component that effectively allows us to say, hey, just run this for me, and it will make the scheduling decisions for us. So it will ultimately look at the pod, look at the cluster, and it will make a decision on where to schedule that. And that's all dynamic and handled for us. And ultimately, the bin packing components of that will come along within Kubernetes in the future. We don't quite have all of that yet. It doesn't quite match all, but it's going to get there ultimately. I just want to mention volumes very quickly. I don't have much time. We need to be able to share state or have state within the cluster. This is provided by volumes, which will be effectively mounted by the containers running inside a pod. And pods, containers within a pod can share that same volume that's mounted. We have multiple different representations of volumes, including an empty directory, which lives within the pod. This is backed by storage, but it's completely ephemeral. When the pod goes away, the storage goes away. So it's used for anything that's transient, temporary storage, that kind of thing. We have a host path. We can actually map a directory on the node itself into a container as a volume. Use this with caution. Often nodes are different. We know that the operating system, the underlying operating system environment may change in such a way that what we see within that host path may differ from node to node. So this isn't necessarily recommended. You can use NFS or GlusterFS and others nowadays to mount a volume. You can also use cloud provider or block or file storage, and this AWS and Google Cloud Platform both provide this facility. So this will map to a Google Cloud Platform persistent disk or to an AWS block storage device. We can also use a thing called a persistent volume claim as well. And these things change one thing about what we talked about before, that they live as long as the pod does. These things can live beyond the life of a pod. And we use them to basically ask the underlying cluster to provide the volume for us. We set out a requirement in terms of size, maybe in terms of identity as well, and it will give us that volume. Where it's possible. It may not be able to. It may have to schedule that. It may be we're asking for a terabyte's worth of disk storage when we don't have a terabyte available. So that request will be queued and will given to us when it becomes available. So persistent volumes effectively isolate us from any specific cloud environment or on-premise environment. Administrators generally provision them and users claim them via these templates and specs we've talked about before. We can also do dynamic provisioning of these as well. So once we ask for a claim, the underlying cluster can provision them for us. They have an independent lifetime from the things that use them. So they live until the user is done with them. You can actually control the life cycle, determine whether they should be recycled or whether they should be reused and handed off effectively between different pods. And they can be dynamically scheduled and managed just like nodes and pods. Clustered applications. So this is a problem that Kubernetes is now trying to address through a thing called stateful sets. With a clustered application such as Cassandra, nodes have a unique identity which is coupled to data on the disk. And nodes may effectively have to be configured and initialized in a certain way or in a certain order. This is, as you can probably imagine, from Kubernetes, a little bit more complicated. So we've introduced this thing called a stateful set. Basically, stateful sets, again, do what we've done with replica sets in the past. They stamp out identical copies of a pod. But they do make sure that each one has a unique identity. And they allow each one of them to have its own reusable persistent storage. And that looks something like this. This is a pod, effectively. It's called DB0. They have ordinality. So part of their name is an ordinal number, in this case DB0, and they are matched to a persistent volume called PVDB-0 in this case. Naming obviously will be different depending on what you're deploying, but they are consistent. And when you create the next one, maybe scale, maybe from 1 to 2, maybe you ask for 10 initially, and it will do this automatically. Or maybe you scale and add new pods. But the next one will be called DB1, same with the persistent volume. And the next one will be called DB2, etc., etc. But that ordinality is important, and that sense of identity is important as well. So basically, you're going to say to the master, I want 3 of these, and it will create 3 for you. The first one will be DB0. It will create a persistent volume claim, and that volume will be assigned either from a new volume that we created specifically for this deployment, or it will give you one that already exists, one with that identity that it understands completely already. And the next one we create, DB1, the same thing would happen. We create a persistent volume claim, and that's matched with either an existing volume or a new volume. And DB2 with the same. And what we can do is, at any point, we can take 2 of those away, but the persistent volume continue to exist. And when we add them back again, they will map to the same volume. So now they have this sense of identity, and they have their own stateful storage. So now we can do things like the clustered applications that we talked about earlier, things like Cassandra. Another component for that is something called initialization containers. So when we spin up a pod, we can also spin up this notion of an init container, which will perform different functions. They basically work till they're finished. They can be used for bootstrapping, effectively. Normally when we have a pod, we build the containers within that pod from an image. That will be called baking. But you can also bootstrap these things by providing configuration based on the environment. So your init container could come up, it can look outside the rest of the environment, make decisions based on that, and then configure the containers, the other containers that will be running based on that environment. We can use this for discovery of peers, using peer finder scripts and sidecars. We can use it for startup and teardown ordering, which is absolutely vital with something like Cassandra, for master elections and also ultimately implicit ordering. And those things are available today. All of that's in beta currently. Init containers and stateful sets are introduced in 1.3. Init containers are beta in 1.4, and stateful sets are now beta in 1.5. I'm going to skip over the rest. I'll provide the slides for you, but you can do configuration. Coming from the environment, provide configuration via a resource. You can provide secrets via a resource. And the last part is multi-cluster federation. Ultimately, we can have our control plane match multiple clusters within different availability zones. So this could be something running on AWS with different clusters or parts of a federated cluster running in different availability zones, or we can also have different clusters, parts of that federation running in different places, in Google Cloud Platform, in Amazon, or on-premise as well. Cluster federation is still a work in process where
Sorry to interrupt, but we've got about 30 seconds left.
Yeah, I'm just about to finish. Okay, cool. So I will share these slides with you. We have a very, very large community. It's extremely powerful. Normally it's messages for people who've never heard it before. And I also mentioned Niantic. We run Pokemon Go on Kubernetes, in case you didn't know. And that's it. So basically that's the entire talk. I've not left time for questions, but you can send them to me via Stan. Stan, is that okay?
Yeah, perfectly well. Thank you very much, Mandy. This was a great presentation.
I'm sorry I didn't leave time for questions, but feel free to just throw them at me and I will do my best to answer them. Some of the questions you've already sent to Stan are a little bit, need me to do some investigation, but I will do my best to answer them over the next few days. If you have any more, send them to Stan, you'll send them to me.
Okay, thank you very much, Mandy.
Thanks a lot. Cheers. Bye-bye.